general systems, so you can use the same things, but you have to know that just how to define this quantity which is seated here. For electromagnetism, this is actually very clear for me that what is this vector. This vector will be, the first component will be density multiplied to the C, and the other components are the normal J. But for the matter field, you have to know that what is the quantity which can contain all together. The quantity which contain all together is called the energy momentum tensor. Momentum. You have it here, rho and the C. So the situation is that finally, if you define a vector, so everything will be fine. But there, you have a more quantity, you have a pressure, you have an energy density, you have another. Some of them are vector, some of them are not vector. So you needed some more general things. So energy momentum tensor is like that. So one day we will back to that, or I will ask you to go and just read at the definition of energy momentum tensor. For the general matter Lagrangian, if they give me the Lagrangian, I can define for you the energy momentum tensor. So there is an algorithm to find the energy momentum tensor. And the component of this energy momentum tensor, some of the coordinate components correspond to the pressure, some of them correspond to the energy density, and some of them. So each component has an interpretation. I mean, I don't want to enter now the technical things of that. So this is the conservation of the energy in a special relativity in general. And inside the T, you have all the information which you think you needed to define a system. For example, pressure is inside that, energy density is inside that, and velocity of the light, even the velocity of the particle is inside of that. So all the kinematics are inside that. So this is actually a kinematic parameter. Kinematic came from the kinematic. And this is, I explained that, this is just to guarantee that the equation will be Lorentz invariant, because it means that the change in all the coordinates should have the same format. One thing I want to tell you is that if you wanted to have a quantity which remain the same for all frames, which remain the covariant for you, I want you think about that. This quantity normally should be a combination of the derivative of the other vectors, or the tensor, or the matrix, for example, something like that. So always, all the quantity or conservation of the energy should come by the some derivative. And not by the first derivative of the some quantity, which is sitting here. So the principle of minimal gravitational coupling say that if you wanted to use the conservation of the energy, this is all was about the special relativity, as you know. If you wanted to have the locally, or if you wanted to keep it the conservation of the energy in some sense in general relativity as one of the fundamental laws of the physics, so locally this equation should not contain any quantity from the geometry. Mainly, it should not contain any type of the curvature, because the geometry for us will be different according to the curvature, according to the change in the, according to the distance which you can connect 2 points over that. So some of the geometry, as you know, have the linear connection as the less distance between the 2 points, and some of them not. For example, in the very early course, like astronomy and these things, you heard that the shortest distance between the 2 points, or even by traveling over the Earth, is not in the linear line. You have to travel by the plane, and you have to pass the curve. Or the satellite, for example, they are using the idea that the space is not flat for us near to the Earth even. So I mean that, okay, forget about that. The conservation of energy should not contain any type of the curvature. So no curvature. I will explain what is the later curvature. No curvature in conservation of the energy equation. I write this equation without any index because I don't want to start at the gymnastics of the index at the first lecture. Later we will see that how to balance the index here. Then the important thing in general relativity is not the real meaning of the quantity, what the mathematicians know. This is the important that how to balance the equation, which gives you the correct physical quantity. So if I know how to write the balance index, so that will be fine for me. So 5 principles actually we propose to build any classical gauge theory for gravity. So Mach principle, equivalence principle, general covariance, principle of minimal coupling. I mean the conservation of energy should not be contained any curvature term. That's all. And then the last one was that the theory should reduce to the Newton gravity in the weak regime. If the theory is not respect any of them, so maybe sometimes it works, but basically we can say that the theory has some problems. For example, some of the new models to correct the general relativity to include the dark energy and dark matter problems, very good theories, they doesn't have Newtonian limits, for example. So they are not able to explain the solar system's physics or the bending of the light. So I want to draw a diagram here. So this diagram is very helpful for us. This first book of the Inverno, is mainly text, as you see. So I will ask you, please go through the text and read it, the text, and there is something we can talk about there. So basically I have, because formally this is the course which goes to the, and so our book was introduction or introducing Einstein related. I have to write it that in the beginning, but and we started from the chapter 9, from that to of general relativity. So, but I will use another things. I will tell you that the next reference you have to read it that because it's not just a part of the book is related to the general relativity. Is the fundamental book of the Landau and Lifshitz, the classical theory of the fields. So I can tell you that I learned the general relativity from this book before to read any other books. But this is a Landau Lifshitz, so it needs a little more revolutionary changing thing actually in the mathematics. Classical theory of fields. So Landau and Lifshitz. So the first chapter is about the special relativity. You can just review, I review